Pretty good. Getting to the end. So let's start with taking a look at what we've got left in our class. So I've just got the last few weeks up here of things that we'll be doing. So we are currently here on the 4th. We'll do shortest path today. Tomorrow is an election day. Then we will do, on Wednesday, we'll kind of sum up what we've been talking about with graphs. And we'll talk about some classic graph problems, some interesting graph problems, and some more applied graphs, and kind of try to bring that all together nicely. On Friday, we're going to, your Challenge 4 will be released on Friday, so we'll spend a little bit of time in class talking about that and going through the things that you need to know to do Challenge 4. Challenge 4 will be comparing two data structures, so what you'll need to know that we haven't done so far in class is just how to measure that on in a C++ program. So you'll be comparing, I think, a binary search tree and a linked list, and so essentially like adding a bunch of elements into that, doing a bunch of operations and timing those operations. So we'll go through kind of the mechanics of that and answer any questions you have about Challenge 4. Next week we will cover hashing. And then at the end of the week and the beginning of next week, we will talk about how all of the data structures we've looked at are applied. And we'll take a somewhat different quiz. We're going to do that on Monday. It's a little bit longer than what we usually take, but it's just, you'll give you scenarios and you'll pick which data structure makes the most sense. And so part of this quiz is part of our ABET accreditation. People know what ABET is? So yeah, if you don't know, ABET is kind of like this separate third-party organization that like universities essentially pay to evaluate their programs and say that, like we're running an actual, program that makes sense for like computer science or computer engineering, software engineering, cybersecurity, whatever it might be. So what we usually do is like, when you graduate, you might have an interview with some people that represent ABET. From time to time, they'll come visit and look at different things. But every course that you take has certain assignments or quizzes that are kind of flagged for that purpose. So this is one of those. It's not anything you need to worry about any more or less than another assignment. But I just wanted to let you know that's why we'll be doing a quiz that's in a little bit different format. After that, kind of the week before Thanksgiving break, we will do our Exam 3 review and take our Exam 3. That will bring us into December, so just for anybody who's wondering, I don't plan for us to have class on that Monday of Thanksgiving break, just because I know some people like to travel a little bit further, and if we can cut out things earlier for you, that's better. And then the only thing we have left after that is we do have a class day on December 2nd. I'm not sure if we'll need that or not yet. I would guess no, but since you'll have already taken your last exam. And then the only other thing that exists on our calendar is if you want to take the optional final exam. And if you remember, you can replace one of your other exam grades with the final grade if it's higher than that grade. So what I'll do is after you take Exam 3, over this Thanksgiving break, I will compute, what your grades are, and then I will get that updated for you on Canvas, and I will let you know if there is a benefit for you to take the final exam. It can't hurt you, but for a lot of you, it won't actually, like if you have an A, there's no reason to take it because you can't change your grade any higher. So that's kind of the rundown of everything we'll be doing for the remainder of the semester. Hope that is helpful for kind of planning purposes. But again, immediate stuff that we'll be working on, finishing up graphs this week, hashing next week, and then kind of a overall review. Are there questions about schedule or? Okay. Does anyone have anything that hasn't been covered in class that you want covered in class? You can think about that. I'll ask you again on Wednesday. If you have any data structure requests, happy to fit them in here. All right, so last time we talked about minimum spanning trees. And if you remember, we had first this idea of a spanning tree, and that is just when we have a graph. This is how can we reach all of the vertices without forming a cycle and not having any redundant edges, so just like the minimum number of edges necessary to do that. Or I'm sorry, for a spanning tree, it doesn't have to be minimized. Just anything that reaches all of them without forming a cycle. Then we move to a minimum spanning tree, where we look at weighted edges. And so we want to do the same thing, but we want to minimize these weights. And so we looked at a couple of algorithms for doing that. If you remember, we looked at Prim's algorithm to find a minimum spanning tree within any graph. And so this was a greedy algorithm. You can remember we stepped through it in an example. Looked like this. This is kind of the pseudocode for Prim's algorithm. And so we were able to explore this weighted graph and to find a minimum spanning tree. And we remember that it provides a minimum spanning tree. That's not always the only minimum spanning tree. We also looked at Kruskal's algorithm for doing this, which is also a greedy algorithm, but this one focuses on the edges and building kind of more than one graph at a time and then joining them together. And this looked kind of like this with the pseudocode there. And this is using a min heap to sort the edges and process them. So I want to go over a couple of reminders for Wednesday's quiz, because it's things that we've not done for at least a week or two. So one of the things that we will have on Wednesday's quiz is the adjacency matrix idea. So if you have, and you'll be given something like a graph like this, right, with these weighted edges, and it's got directed edges. And then if you're given like a table like this, a matrix, and in this case, we'll say that these rows are from, and these columns are to. And so essentially we want to go from that visual representation to this tabular form here. And so if you remember, we discussed the way to do that. So in this case, like we would start, let's just say we're going to start with the from side here and say A. So A can go to B with a weight of 2, A goes to C with a weight of 4, and A goes to D with a weight of 4. And then A doesn't go to itself, and A doesn't go to E. So I just put a little dash there. You could put nothing there or null or whatever. So that's the basic idea of making an adjacency matrix. So in a similar way for B, you can see that because this is directed, right? So going from B, we don't go anywhere. So there's nothing on this row. Yes?
If these weren't weighted, would we just do like 1 and 0?
Yeah, absolutely. If there's no weight, yeah, it's kind of just like a binary, is it there or not? For C, so you can see that C has 1 outgoing to E, right? 5 there. And then we keep going. D just goes to E with a 1, and E doesn't go anywhere. And so that would be an adjacency matrix for a weighted directed graph. Does that make sense? Is that okay with everyone? Okay. So now we talked about a couple of different representations. This turns out to be one of the easier ones to write down on an exam. So if it was a weighted but undirected graph, so the arrows are gone now, same weights, right? In this case, we don't really care, like to and from don't have much meaning, but we can look at it the same way. So we can say that A is connected to B and C and D with these weights. And we can say that B is connected to A, since it is undirected. Same thing with C. You can see it's connected to A and E, and D, and E. So if it's unweighted, you'll get this kind of representation. Something with this that you will notice for an unweighted adjacency matrix, right? There's symmetry here, right? So you could fold this along this line and they would be the same in those cells. And that makes sense for this undirected graph, right? Because they share these edges. Not great if you're storing it, because you only need half of the space. But. And then, yeah, there's your question. So if you have an unweighted and undirected graph, for example, you could do the same thing just with like a check or a 1 if the edge is there. All right. So the other thing that we will have on the quiz is depth first search and breadth first search. And so let's refresh on that a little bit. So if you remember depth first search, the idea is that we explore each kind of possible path as far as we can. So like with this figure, we have a graph that's, let's say we start at A, for example, and A has neighbors B, E, and C. And if we're going in this arbitrary order, we might go to B, but then we're going to go to B's children all the way down, and then come back, and then go all the way down, and then all the way down. So the idea is that we're going all the way as far as we can before we go anywhere else. And so if we were looking for X, right, we might end up going all the way down here, then all the way down here, then all the way here, and then stopping when we get to X. We don't need to go any further. So what that looks like, kind of at a code level. So for this graph here, let's say that we're going to start at A, and we're going to go to G. And so we will call DFS on A and the target of G. And so the first thing we'll do is find our neighbors, which are B, C, and E. And so we'll call DFS on B here. And so I've specified that I'm going to process the neighbors in alphabetical order. When you're implementing this, you may do that, or you may just do kind of whatever naturally comes first. But for this purpose, we'll do it in alphabetical order. So I got B, C, and E. I'll do B first. And so on B, B doesn't have any neighbors. So then I'll come back up and do C. And so C does have neighbors. It has D and E, right? And so going alphabetically, I will go to D next. And what should I get for D's neighbors? F, yeah. So D has one neighbor, that's F. So I'll go ahead and go to F, and then F has one neighbor, which is G. And at this point, if you remember, we were actually looking for G. So we've found G, and that means that we've got a path. And to get that path, all we have to do is kind of pop back up this stack that we've come down. And so you'll get a path that looks like this. So in this case, A, C, D, F, G will be a path from A to G. And if you remember with depth first search, you will get a path if there is one. It is not necessarily the shortest path in number of edges. Questions about that? Okay. So let's compare it to breadth first search. So if you remember with breadth first search, we kind of do this a layer at a time. It's kind of like an expanding frontier, sometimes you'll hear it called. So like we would start and we would start at A, and then we would say, okay, A's neighbors, we visit B, E, C, and then we would do the next layer of that for B, and then for E, and then for C. And so you'll get to your target at a different point in time, essentially, is what the important thing is here. So let's walk through it. So with breadth first search, we keep a queue running, and we insert neighbors into that queue and then process from that queue. So we'll start, same thing, we're going to go from A to G. So the first call we call breadth first search with A as our starting point, G as our target. We find out that the neighbors are B, C, E. And so we add those to our queue. And then for our next step, we take an element from the queue. So in this case, that's B. And we call breadth first search on B. And so we get B's neighbors, which it doesn't have any neighbors. So we don't do anything. We go ahead and get the next thing from the queue. And so we get C's neighbors. Who are C's neighbors? D and E, yeah. So D and E come through. Now E is already in our queue. So we add D to the queue. We don't add E. And then we process from the queue, E in this case. And so we go to E, and we ask E for its neighbors, which gives us G. Depending on the implementation, you may detect it at this point, or you may go a step further before you detect it. We'll say we detect it. And so that will give us a path of AEG here. So same graph, two different algorithms, two different paths. Remember, with breadth first search, the nice thing is it will always be a shortest path in terms of the number of edges. Questions about breadth first search? Okay. So here's the comparison, kind of the high points here. You can see our depth first search path going around this way, and then our breadth first search going more directly that way. Neither approach is better all of the time. So you kind of need to know something about the data that you have to choose which one will be best on average. But in the worst case, they are the same. So for the quiz, we will do one adjacency matrix, one depth first, and one breadth first. And I will make the graphs as small as I can make them while they're still meaningful, so that it does not take us forever. So just be ready for that. And if you, before class on Wednesday, you can just look at these slides real quick. I think it's pretty simple for these small graphs, at least. Okay. So finally, today let's talk about shortest path. So if you remember, we just saw breadth first search will give us a shortest path in terms of the number of edges or vertices we go through. But that doesn't help us when we have a weighted graph. Now, there is a trick we could use if you wanted, for example, to use breadth first search on this weighted graph. Does anybody have an idea of how you might do that and have the weights have meaning still?
Try the lowest weight first.
The lowest weight first? Yeah. So that's kind of where we'll get to eventually today is something like that. So I'm thinking of a little bit of a simpler approach. How could we convert this graph into something that breadth first search would give us a shortest path for? So if you look at the edges, like say, we know breadth first search can't process these weights, right? But it can process like number of edges, right? It can optimize on that. So if instead of say like a 2 here, what if we just added a couple more nodes and made this path 2 longer, then 4 longer? So we add to the graph, right? So that's one way you could go about it. And in some cases, that's okay. It doesn't make things horrible computationally. But in the general case, it does make things horrible. So it's not a workaround that we could use all of the time. But you could see kind of logically how that can work, because breadth first search is able to optimize on the number of edges and vertices that it goes through. If we just make these weights the equivalent in vertices and edges, then we can solve it that way. But we're going to look at a better way to do this. So if we were to run a breadth first search on this from A to F, we might get something like this, right? Because it will minimize the number of edges that we have to travel through. And I don't think there's any way to get from A to F with less than 2 edges. So 2 edges is a pretty good solution. But if you add up the cost here, right, 7 plus 2 gives us 9. So that's our total cost from A to F. Do you see a route that gets us less than 9? Yeah. So even though it's much longer, right, if we come around here and we go from A to D to G to H to F, we can do that with a cost of 6. So we've gone through more nodes, right, more vertices, but our cost is lower. And so when our edge weights matter, which is in a lot of cases, a lot of practical applications, then what we care about is not how many vertices we go through, but what the cost is to do it. So in this case, we would much prefer this path to this path. And so the question is, how do we get that path? So the answer is going to be something called Dijkstra's algorithm. I don't know if you've heard of Dijkstra's algorithm. This is Dijkstra himself. He's a relatively modern computer scientist. He passed away in 2002. He's a Turing Award winner. And he was a very opinionated guy. He's written some really, really interesting and influential things within computer science. One of the major ones, and the one related to his Turing Award, was an essay called Go-To Statement Considered Harmful, and kind of changed the way that we write software into using what's called structured programming then, what now we kind of just think of as programming probably. But I don't know if have people seen a go-to statement before? Ever experienced that? Okay, so this is kind of like, if you ever write like assembly code or anything lower level, you have these statements that tell you, like you're executing lines of code, right? And then you'll get to one that says just go to line whatever and start executing there, right? And so, believe it or not, this used to be a really common way of programming things. And so even like several, I guess, recent, within the past 10 years, like major security bugs have been due to using go-to statements and things like that. So there were a lot of reasons to consider a go-to statement a bad idea. It's definitely something that was popular because of how we started programming, which was obviously at a very low level, working our way up to higher level languages. I don't know if a go-to statement is still supported. It's probably still supported in C, depending on what you do. But anyways, the idea is that you can kind of bounce around and just start executing at an arbitrary point in a program, which you could see why that could be a problem if the code has a bug in it. But what Dijkstra is most famous for is Dijkstra's algorithm. And Dijkstra's algorithm is a greedy algorithm that will get you the shortest path on a weighted graph. And so, kind of at a high level, this is the idea of Dijkstra's algorithm, is that we're going to find the minimum weight between vertices in a weighted directed graph. And the way that we're going to do that is we're going to keep track of the best known route to each vertex, and then as we explore the graph, we will update the best known route if we find it. So there are a ton of applications for this, obviously. Anything where you have a weighted directed graph. A good classic example is just that you have like cities as the vertices, the edges are distances between the cities, and you want to find the shortest path, the shortest distance between any two cities, right? So, looking at this at a little more of a pseudocode level, we can define Dijkstra's algorithm as taking a vertex start and a vertex and end. We're going to track the cost for each vertex to get to it. And so initially, we're going to say everything has a cost of infinity to get to. We're going to use a priority queue, and it's going to be ordered by the cost. And so initially, we will set the cost of our starting point to 0. and then we will put it in our queue. Then what we're going to do is we're going to process the queue continuously. And it's important to remember it is a priority queue, so it maintains a sorted order. And so what we'll do in our loop is we will take whatever the minimum vertex is, we'll mark it as visited, and then for each of its unvisited neighbors, we will compute the cost of going from it to its neighbor. And the way we do that is we do the cost that it took to get to it plus the cost it would take to get from it to its neighbor. And if that's less than what we currently have down for that neighbor, then we're going to use that value. So we're going to update anywhere we stored that to be this new value. And we're going to store that, in this case, n is the node before that we had to go to get this weight. And so that's important for reconstructing the path later. But we'll just do that in a loop. And then when we're done, we will have the shortest path. So this will be, like with most of these, it's easier to look at an example of this to get a feeling for it. So I'm going to start with this directed weighted graph. And I've got a queue, so that's a priority queue up top. And we could implement that with a min heap. And then I've got just an array over here. And so for each node that we have, I'm going to keep track of if it's been visited, the cost to get to it, and what node I came from to get to it. And so in this case, let's go from A to F. So the first thing we're going to do is we'll go ahead and initialize all of these costs. We'll set them all to infinity initially. However, we're starting at A, right? So the cost to get to A is 0. We start there, right? And I'll go ahead and put A into the priority queue to be processed. So the next step is to process an element out of the queue. So I pull A out. And so the process of processing A here, so the first thing I want to do is find the neighbors of A. And so in this case, we're in a directed graph. So our neighbors are B and D. And I'm going to compute the cost to get to B and D from A. And so that cost is the cost it took me to get to A, which was 0, plus the cost it takes me to get from A to D. So in the case of B, that cost is 0 plus 2, so that's 2. And in the case of D, it's 0 plus 1, that's 1. So currently, if we go look at our cost, prior to calculating that, the cost was infinity. So obviously 2 is better than infinity, and the same case for D, right? And 1 is better than infinity. So at this point, what we do is we go ahead and update the cost for B and D to the cost we calculated. We set the previous node for those to A, so that's where we're coming from. And then we insert into our priority queue D and B. And that is the full thing that we need to do to process a node here. So at that point, we can mark A as visited here, and we can move on to the next item in the priority queue, which in this case is D. So we pull D out of the priority queue, and the first thing we do is ask D for its neighbors. It's quite a few neighbors, as you can see. So it's got C, E, F, G as neighbors. And so for all of those neighbors, so C, E, F, G, you can see before this step, they were all infinite cost, right? So we're going to compute the cost for each of them. And in this case, that's going to be the cost of coming from D to each of the neighbors. So if you remember, to get from A to D, that was 1. So we do have a D, a cost of 1 here. So our new cost will be 1 plus whatever it takes to get to the neighbor. So for C, it'll be 1 plus 2, just 3. For E, 1 plus 2, 3. F, 1 plus 8, 9. And then 5 for G. And so we will update those cost values here for all of those nodes. We'll set their previous node to be D, since that's where we're at currently. And we will put them into our priority queue. Does that feel okay so far? Okay. Keep going. Okay, so we had B as the next element in our priority queue, so we'll pull out B. Same process will happen again. We will ask for the neighbors of B. And so for B, we have the neighbor of D and E. Now, D is a little bit different because we've already visited D. So because we've already visited it, we just ignore it. We already have the optimal path to it. We don't need to do anything there. So D is just ignored. So then we will look at E. And so if you look at the cost for getting to E, it'll be the cost of getting to B plus the cost of B to E. So that's 2 plus 10, which is 12. And currently, it looks like E has a cost of 3 to get to it from D. So that's lower. So we have not found a better path here. We will just leave that as it is. So we're just going to ignore that because our cost is higher to get there. So there's no neighbors to add to the queue, nothing to update. So we can mark B as visited, and we can move on to C. So processing C, same thing. We have C here, and we ask for the neighbors of C. Since this is directed, you'll get the neighbors of A, F, and H. You can see that we've already visited A, so we can disregard it. So that brings us to F. So let's go ahead and compute the cost there. So for us to get to C, which we came through this way, at a cost of 3. So from C to F is 5. So 5 plus 3 is 8, which currently our cost of getting to F was 9. So 8 is better. We will go ahead and update that. That's now 8, and its parent or its previous node is now C. For H, the cost is 13 plus 3, which is, it was currently at infinity, so of course 16 is better. So we will update that. Actually, that should be in the wrong. I'm going to fix that while we're here. So that's H should be like that. All right. And I'm sure that will propagate. Okay, so let me just once more go through that. So we were computing to go from C to H, so 13 plus 3 is 16, which is less than infinity, so we'll update H, not I. Okay, so next step, we're going to pull the next element out of the priority queue, which is E. So we go to E, we ask for the neighbors of E, which is just G in this case. So the cost of us getting to E is 3. So the cost from E to G is 6. So 3 plus 6 is 9, which it looks like for G we were able to get there in 5 if we came from D. So we won't update that. That's already got a better weight. So we've done everything we need to do here. We can mark E as visited, and we can go to G now. Go to G, same thing. G has one neighbor, F. So if we compute, so it took us 5 to get to G, and it takes us 1 more to get to F, so that's 6 to get to F. And we can see that F was currently, it took 8. So 6 is better, so we'll change it to 6, and we'll say we're coming from G. And so we update F, and so F was in the priority queue, so that's something to note. When we update this cost, right, if this element is also in that priority queue, we have to change it in that queue, which could change its position in the queue. So that's something to be aware of there. But we change it in both places, and so that means F will be the next thing that we process. So F comes out, again, the exact details of detecting this, because it is our target, depends on the implementation, but roughly as soon as you see it. And so at this point, we have our goal. We can go ahead and reconstruct our path. So to reconstruct our path, what we do, so F is where we ended, right? we go to see what was the previous of f, and we're told that's g. So we go to the entry for g. The previous for that was d. We go to the entry for d. The previous of that was a. And we go to the entry for a, and it has no previous because that's our start point. And so that is our path backwards. Flip that around, and we get ADGF as our path. Questions about that? Yes?
Yeah, negative weights.
That's a good question. I think with Dijkstra's, it depends on how you implement it. So if you want to talk about detecting a negative weight cycle before you do this, yeah, and then you don't do this. Bellman-Ford is a more general algorithm that will handle negative weights on the path, but yeah. Yeah, so I believe Dijkstra's, and I'll check on this to be sure, is only positive weights. Now, there are ways to manage negative weights, such as normalizing the graph, if that's possible, right, just to get rid of the negative weights. But yeah, so that does matter whether you have cycles and whether you have negative weight cycles. Yeah.
I was just thinking, like, with this, if you have negative, you theoretically could just get trapped and get into a shorter,
Yes.
shorter path.
Absolutely, and that's a great point, because this is a greedy algorithm, right? Like it just is going for that local best over and over and over. And so yeah, if you got into a negative cycle, you would never come out of it. Just kind of dark and sad. But yeah, I know for sure that Bellman-Ford will handle that case, and you can detect it using like depth first search techniques kind of to mitigate it. But yeah, it's a good point. Okay, so Dijkstra's algorithm is a greedy algorithm. It always chooses the best option locally, but it does produce the optimal result, and the reason is because at any time in its execution, these two things hold true for either visited or unvisited vertices. It keeps the path cost the lowest possible. And so because of that, it does give us an optimal result, which is not always the case with a greedy algorithm. It is a case with Dijkstra's algorithm. So the complexity for Dijkstra's algorithm, it depends on how you implement it, right? So these are three common ways of implementing it. And if you kind of just go with the basic array approach, you'll come out with something like big O of v squared, v being the number of vertices. If you can get better, if you use, like we talked about, the priority queue as a min heap, you remember that the operations on the min heap are a little bit better. I won't go too much into this, but essentially what you will come down to is something that can reduce to order of E log V, E being number of edges, V being the number of vertices. You can do a little bit better, so depending on the type of graph, right? If you use something called a Fibonacci heap, which we didn't talk about, but is a really useful data structure. If you have a dense graph, technically, or theoretically, a Fibonacci heap is a better way to do this. And you can see these, like V log V plus E versus E log V. The trade-off is in if you have more edges and less vertices, that kind of thing, so dense versus sparse. This priority queue approach, is for the general case and for sparse graphs for sure, is the best. The Fibonacci heap, in theory, would be better for a dense graph, but the implementation of a Fibonacci heap kind of has like overhead associated with it typically, and so that can actually kind of overpower the advantage you're getting. So in general, kind of the implementation you'll see is this priority queue min heap based implementation. And so this final kind of big O is a result of a reduction here. Because the graph is connected, we can make some of these substitutions. But it's just kind of important to know that the implementation here does make a difference, obviously, in terms of the complexity. Oh, and I should say, we didn't use the term when we were talking about it. You'll see it in here, relaxation. So if you say you're relaxing an edge of the graph, all that means is that you're updating that shortest path for that node. You'll see that language used in a lot of the theory text. All right. So let's go through one more. And we'll go from E to H this time. So we will start by initializing everything like we do to infinity and putting a 0 at E, and it has no previous node. So we will then pull E out, and we will say what are E's neighbors, G and B, right? So in this case, we will update the cost of G and B to 80 and 30 and set the parent to E, and then we will add those to our priority queue. And you can see, like obviously the priority queue is a min heap, so 30 gets to go first because it is the lower of the two. So then we can process G at this point. Same thing, we get its neighbors, which for G, you'll see in this graph I have a few edges that are bidirectional. That's fine. We can handle that. We just follow the same algorithm exactly. So for G, we look at all of its neighbors. We do our computations there. And you can see we have D and A with their associated costs of 50 and 150. And we add those to our priority queue. So that actually puts A in the front of the priority queue at this point. And so we can now process A next. So we'll go to A. We'll look at A's neighbors. And in this case, A has neighbors B, D, and G. And so G we've already visited, so we can kind of just ignore. We won't need to do anything there. But for B and D, we'll compute the cost. Those costs are better than the costs that were already in place for these. And so we will update those to have their previous node as A, update their cost, and we'll update them in the priority queue, most importantly, before we decide to pull another element from the priority queue. So at this point, we'll pull B out of the priority queue. We'll get B's neighbors, and we will look at those. We've already visited A, and let's see what else we have. We have F. So we compute the cost for F, and we get that is 80. So we'll go ahead and update that, set the parent to B, put it in the priority queue where it's the first. So that will give us, this should say F, I believe. We'll process F at this point. Here we go. And we'll get F's neighbors. We'll compute the cost of F's neighbors. So F has a neighbor of C and a neighbor of D. Right? We will compute those, compare them to what's here, and update as needed. And so that will give us the priority queue having D and C at these values. So we will pull D out, and we'll do the same thing for D. We've already visited F. We can ignore that. Let's see. We've got C is its other neighbor. So we'll compute for C. We get 130, which is less than 150. So we'll go ahead and update that both here, where we'll update this to be D, and then we'll update C's priority queue value too. We'll process C, and we will find its neighbors, which H is one of its neighbors, and D is another neighbor. D is already visited. We can ignore that. For H, we will compute the cost, which is 150, and we will add that to our priority queue. We'll update it here in the table as well. And you remember H is what we're looking for here, so E to H. And so at this point, we have made it all the way through. We've got our table of values, and we can compute our path. And if we work our way back up from H, we can see we go to H, we'll go to C, which will then go to D, which will go to F, which will go to B, which will go to A, which will go to G, which will go to E, and E is where we started. So a bit of a long path there. You flip that around, you get that nice path there, and that is the lowest cost, shortest path. So that is all I wanted to look at today. On Wednesday, we will look at kind of broader graph problems and their complexity, and we will do a quiz on an adjacency matrix, breadth first and depth first search. So we'll see you then.